All right, ladies and gentlemen, welcome back to your favorite class. Rawr! This week, new stuff. All right, no more kinetics. Hopefully you had your fill of kinetics with that last homework, okay? So homework 3 was due today. Hopefully you got that in. If not, what are you doing? First simulation, reminder, is due this upcoming Friday. Had a lot of questions on that, so please keep them coming. If you want to come to office hours every single day, 9 to 10, and Tuesdays and Thursdays, I have additional hours, 8 a.m. to 9 a.m. All right, so come to office hours, ask questions. If you don't know what you're doing in MATLAB, come see me. That's that. Next, I've posted a new homework. It's homework number 4. It's going to be on material that we cover this week. You'll probably be able to start in on it maybe after tomorrow's lecture. Probably won't have a lot of tools in your tool bag quite yet after today's lecture. All right, I got a question. Nope, just the meeting has started. Well, if there are no questions, that's all the announcements that I have for now. So if that is the case, then onward with material. All right, the topic today is work and energy of a rigid body. What's nice for me is you have seen work and energy methods already. Hopefully you did a lot of work and energy stuff with your particle class in 2002. So I have a series of notes on general particle work and energy at the beginning of the slide deck that I handed out. And I'm actually going to kind of gloss over most of that pretty quickly in the next, 30 minutes or so. So in the next 30 minutes, I'll kind of be pushing through the material that are in those first few slides, but the material that are in those slides is much more detailed than what I'm going to do right here. So if you need a little bit of refresher on work and energy of a particle, things like what is the work of an external force, or what is kinetic energy of a particle, or potential energy of a particle, because those things have slipped your mind, I would encourage you to go back and review those slides. I'm going to go through a little bit of a review of that material now. And just like I've been doing for this class since day number 1, we're going to make some analogies between what you learned in 2002 for particle work and energy and relate that to the work and energy of a rigid body. So we'll make some analogies between linear energy and angular energy, and we'll make some analogies between individual particles and the energy of a whole body, which is basically a mass of particles. All right, so we'll start first with sort of a review of the conservation of energy equation, which applies both for particles and for rigid bodies. So review first will be the conservation of energy equation. Maybe you have seen this with different variables, but I'll roll with the variables that the book uses. So hopefully you've seen variables like this before. And that general equation, which is one that we're going to continue to use over and over in this class, is something like T1 plus V1 plus U 1 to 2 equals T2 plus V2. All right, hopefully you have all seen this equation before, and we will use this over and over and over. You will write this on your papers often, right? So let's define some of these things. Where for a particle, I'll be specific here, we have that T is kinetic energy, typically given by the equation T is 1/2 mv squared for a particle, where m is mass and v is velocity. All right. Next is V, which is the potential energy. Oh, handwriting. And you probably broke this up into 2 different sort of potential energy components, a component from gravitational potential energy and a component from elastic potential energy. So I'll say generally that this V is some portion from gravitational potential energy, Vg, and some portion from elastic potential energy. Okay, so here this is gravitational, and this here is elastic. All right, where this Vg is the potential energy due to gravity, which, going back to probably your high school physics days, you know to be something like mgh, where h is the height of your particle relative to some datum that you define. And then here, plus we have elastic energy. Now, elastic energy can take many forms. Those of you that have taken the mechanics class, so that is ME2004, you've probably seen elastic energy of solid bodies. So if you put some force on a body, it has some elasticity to it, and there's some energy associated with that. But in this class, we're sort of assuming rigid bodies, so there's no energy associated with elastic deformation of our bodies. Instead, really the only elastic energy that we have in this dynamics class is energy from a spring. So here, elastic energy is coming from a spring, where we have 1/2 spring constant K times x squared, where x is the stretched minus original length of the spring. So let's define some of these things. All right, where here this K is spring constant. And this X is the stretched length of spring. All right, you might see it as X equals L minus L0, where L0 is the original length of the spring and L is the deformed length. Okay, so that's your potential energy. And finally, you have work of external forces, which is U1 to 2. This is work of external forces. And I'm not sure which definition that you had for your dynamics class. I'm going to give the most formal mathematical definition, and we'll talk about it a little more in just a second, where we say here that the work from position 1 to position 2 is the integral from location 1 to location 2, A1 to A2, multiplied by the vector F dotted into the position dr. Okay, so this is the most formal definition. You may have seen this in your class as something like from x1 to x2 of fx dx plus integral from y1 to y2 of fy dy plus integral from z1 to z2 of fz dz. All right, it's basically the force over the path that that object has moved. All right, so I'll give a little bit of an example in just a second, but this is the basic idea. All right, so these are kind of the potential energy components, kinetic energy components, and work of external forces that all go into this general equation here, where we see subscripts like 1 and 2 denoting the current state of our particle. All right, so this more or less is the state of particle 1. And this here is the state of particle 2. All right. Hopefully this is sort of ringing some bells. You probably did a lot of example problems with, like, I don't know, pushing a crate along the ground and there's some external force, there's some force from friction. What's the work of that external force? Or maybe particle moving from up here to down here. What is the gravitational potential energy associated with that? Like a lot of these just kind of general things for particles. All right, so let's dive in on some of these a little bit more. I think the kinetic energy, this guy here, is pretty straightforward. Understanding that the kinetic energy is 1/2 mv squared. I think the potential energy, those are usually pretty straightforward here too, that there is some energy associated with a particle that may be at some elevated condition. And here, this is, I think, also pretty straightforward. which is the energy associated with the spring. So as I compress a spring, it's storing energy because it wants to return to its original length. So there's the potential for that spring to do work on a surrounding body. So I think that's sort of easy to understand. A little bit more complicated and more convoluted is this idea of like work of external forces and how those sort of contribute to maybe motion of a particle or the energy that's stored inside of a particle. So I just want to like spend a little bit more time on this like work of external forces, not only talking about work of external forces on a particle, but how we might extend work from forces on a particle to our angular analogy, which is work of moments on a rigid body. All right, so let's spend a little time talking about the work of external forces. And we'll start with a particle. And I'll kind of start this off with what I think is kind of the classic example of work of a force on a particle, and that is pulling a crate with a rope. All right, so start it with an example. And that is pulling a crate. All right, so if we think about pulling a crate along the ground. All right, so here's the ground. All right, there's my ground. I've got a crate over here. And let's say that the center of gravity of that crate is at, let's say, location A1. All right, and I want to pull on that crate to move it to some other location. So let's say that we're going to move it in this general direction, and it's going to move to over here, what is location A2. Okay, and so we want to move that box from A1 to A2, and we're going to move it over a distance which is defined by the length L. All right, so we know that like boxes that are sliding along the ground are more or less modeled as particles, right? So box is a nice example of like a particle that's moving in space, that sort of the dimensions of the box not really that critical for us. But okay, let's say that we're pulling this guy with a rope and we're pulling it along sort of the ground such that we have sort of an angle that we're pulling this guy along. So if we give the force on this guy as F, and the angle with which it acts with respect to the horizontal here is the angle theta, then let's say we pull with force F from location A1 to A2. Okay, well, if we go back to the definition of what it is to have an work of an external force, that general definition that we saw previously was something like this: work of an external force, U1 to 2, is the integral of the path, so going from location A1 to location A2, of the force F dotted into the path dr. Right? So the path here is from A1 to A2, and let's give ourselves a coordinate system here. So we're typical coordinate system here, x, y, so we can sort of define some things. If we want to do this in rectangular components, which, like, why wouldn't we? Then you can write this fully as U1 to 2 is the integral with each of the individual directions having its own equation. All right, so here this will be like x1 to x2, the force in the x direction in x. This is what the dot product generally is. Here we're looking again now in the y direction from y1 to y2 of the force in the y direction dotted in the path dy, plus here going from z1 to z2 of fz dz. All right, so this is just the general expression for work of an external force, kind of in a sort of a three-dimensional sense. Now let's look at one of these guys in a little bit more detail. Well, our bounds is probably where we want to start with. So if we're looking at the path of this particular box, moving from here to here, well, it's only moving in the x direction. And if we say that this is location x equals 0, then our x1 here is 0 and x2 is L. Okay, so we're going from 0 to L, right? The bounds on our other two integrals are more or less nothing. Okay, so if I'm starting at location y1, which let's say that just generally this little datum here is defined as y. So I'm starting at 0 and I'm ending at 0. Okay, well, this entire thing is going to be 0. Same idea for z. I'm not moving in and out of the board, so that component is 0. That means that in this general particle example, we'd have something like the work of this force moving from 1 to 2 is the integral from 0 to L of the component of the force in the x direction. All right, well, here that's just going to be this force resolved into its x direction. All right, so that'll be something like the magnitude of F, or I'll just write it as F times cosine theta dx. All right, so if you're looking at what the work of this force is doing as we're moving that box from the left to the right, then doing this integral, assuming that force is constant, this will result in something like FL cosine theta. All right, so that's just kind of a sort of the classical example of how we look at forces on a body providing some external portion of work. All right, and I started with kind of a three-dimensional sense by doing this F dot dr dot product, which is kind of the most formal way to do it, though you may have probably just seen it as like F cosine theta is the work. So I just want to be sure and be clear about mathematically, sort of like where this is coming from. Now, one last thing that I'll add is if this box is moving sort of from the left to the right, that there may be some friction force that's sort of like opposing that motion as you go, right? So there might be a frictional force that is sort of opposing the motion of that box from the left to the right. And if that's the case, well, you just tack that on as part of this integral because it's in the path of x, but it's in the opposite direction. So you would subtract off the friction force, and this would end up being minus whatever the force of friction is, typically mu k times the normal force. All right. So that's the general idea for how we would incorporate frictional force resisting the motion of that particular box. All right. Now, this is all sort of our linear forces creating external work. All right. So we saw these linear forces creating external work on our particle. Now, we've talked a lot about the analogy between sort of this linear whatever it is we're talking about, how that relates to angular whatever it is we're talking about. So we've done it a lot with the last couple of lectures with kinetics. We talked about like sum of the forces is ma. What is the angular analogy to that? Well, that is the sum of the moments is ig alpha. Okay, so I want to motivate a little bit next with what is the angular analogy. For rigid bodies. All right. So we have external work done by forces on an object. What about external work done by moments on an object? Okay. In work of an external moment, when we talk about moments, we have to have some volume for this to work. Okay. Moment on a particle, not really going to generate a lot of work, and I'll talk about what that is in just a second. But so this must be for a body with some volume. All right. And I'll motivate this again with what is the classical analogy now, not for linear forces, but for this like angular analogy. And so here we'll motivate with an example using a disk spinning disk. Okay, so just like we had the box example where the box is sitting here and we want to pull on it to get to some linear position down the way, we might have a disk that's spinning about some central axis. Okay, so here's its central location, and it's spinning about this pinned location. All right, so the example here is the spinning disk, and it's starting at angular location, which is theta 1, moving to location theta 2 with applied moment m. Okay, so with our disk here, maybe we've got a point on this disk, let's call it point A, and it's going to move from its angular position, which if we define this sort of as like theta 1, it's going to move to some other angular position later because it's spinning. So this is A1. This is going to be some other position later. Let's call it A2, where we have now spun about this guy to location, angular location number 2. So kind of spinning. Oh boy, it's hard to do. Such a slippery writing pad. All right, all the way, for crying out loud. You get the point. All the way here. I can't go on the outside. It's too far. I can't do it. All right. So from theta 1 to theta 2. And to do that, we have to, much like we dragged the box across the ground, to do this, we have to spin the disk with some applied moment. So we're going to apply a moment to this guy, which is something like this. All right. So let's say that that moment is being applied so that we can force the disk to go from A1 to A2. Okay. So then work from 1 to 2 is the following. Here it's this integral going from, again, A1 to A2. But now here, instead of f dot dr, we have what is m dot d theta. The moment applied dotted into the angular path upon which we travel, right? So this is the general idea here. This is the three-dimensional version, much like here, this is the 3D definition for f dot dr. So this is the three-dimensional version, but in this class, we're going to kind of reserve ourselves to 2D. So the 2D version is very simply from theta 1 to theta 2 of m d theta. All right. So that's the general idea there. Meaning that if we sort of had a constant moment, so if m is constant, then this integral would simply shake out to be that u1 to 2 is m times position theta 2 minus position theta 1, or what you might see as m delta theta. All right, so that's the external work associated with moments that are applied to a rigid body. So this is your general definition that you want to have sort of in your head for this class, right? This is the two-dimensional version, and up here, this is the more formal three-dimensional version. All right, so here this is 3D, and this is 2D. And so this three-dimensional analogy is the analogy for what is u1 to 2 for linear forces of integral of f dot dr on the path a1 to a2. Okay, so that's sort of the angular analogy. If you want to dive in on that a little bit more, there's a more thorough derivation in the notes. Okay, so I think it's slide 4. Yeah, it looks like slide 4 in the notes. So I would look there if you want. All right, but the point is now that on rigid bodies, we may have both forces and moments acting. So work of external forces and moments is given by the combination of the two. So we can have external forces moving our rigid body from location 1 to location 2, and we can have external moments that rotate our body from angular position 1 to angular position 2. So the work of external forces and moments from 1 to 2 is, in 3 dimensions, this integral from position A1 to A2 of the forces dotted into the position, plus the integral from position A1 to position A2 of the moments dotted into the angular path. So this is sort of the full-blown 3-dimensional version. All right. But in our class, usually we'll simplify this down into 2 dimensions. And so in 2 dimensions, you'll have something like this integral will shake out to from position x1 to x2 of the force component in x along the direction of x, plus here the integral from y1 to y2 of the force components in the y direction over the y path. So these are kind of the forces in the x, forces in the y, just like when we did kinetics, we had some of the forces x, some of the forces y. And then now plus whatever work might happen about from the moments as we rotate from position theta 1 to theta 2 with moments in the z direction, right? Since we're rotating sort of in this out of plane manner, times d theta. So this is your 2-dimensional version that you will be using sort of in this class. All right. So this guy is probably the guy that you want to give sparkles and, you know, he's special. He gets a party. All right, so this is our 2-dimensional version. You won't find this general form of the equation on the equation sheet. So maybe when it comes time to taking the test, you might want to have that one kind of at the ready. All right. So that's work of external forces. All right. Work of external forces and moments. All right, so that's external forces. Now, the next thing that we kind of need to dive in on is the next sort of term in this equation that we want to talk about, which is, you know, the kinetic energy of a particle. Now, what is the kinetic energy of a rigid body? So the next thing we're going to talk about quickly is particle. So we'll review. We've talked about our external forces. Now let's talk about our kinetic energy. All right. So kinetic energy of a particle typically will be given by, and I'll just write this here, 1/2 mv squared. Or if I have some particle over here, it's got a mass of m, and it's moving along this general direction with v, then v squared here in this general equation is the magnitude of the velocity. Okay, hopefully we all sort of like see and understand that. All right. Now, this is the very simplistic sort of non-mathy 2-dimensional version of this equation. Okay, so here is your kinetic energy of a particle. This is sort of the plebeian form. All right, the cheap dollar store version of this equation. All right, so let's recall, if we can, that the magnitude in rectangular components, the magnitude of the velocity is the sum of the squares of the individual components, which we remember is something like the square root of what would be Vx squared plus Vy squared plus Vz squared. Okay, or if we say that the velocity up here has Vx I plus Vy j plus Vz k. Okay, so this is writing our velocity in our rectangular components, all right? Something you're very familiar with or should be at this point. Okay, so we notice here that the velocity is the sum of the squares of the individual components. Or we could write this as the magnitude of the velocity squared is Vx times Vx plus Vy times Vy plus Vz times Vz, right? Now, you'll notice here that the magnitude of this particular velocity appears in the kinetic energy equation, which is sort of up here, right? So we could replace this magnitude of velocity squared with v times x, vx times vx plus vy times vy plus vz times vz in that equation, right? But what you'll want to know, and if you're sort of fluent in mathematics, which if you're an engineer, you should be, all right? If you're fluent in mathematics, you should identify what this is straight away. And this here is the dot product of the vector v with itself. So this here is dot product of v dot v, right? So the x components multiplied together plus the y components multiplied together plus the z components multiplied together. That is your definition of the dot product, all right? They're individual magnitudes and rectangular components. So while you did get this nice dollar store version of the kinetic energy equation, there is a much more mathematically sound version of this equation, which uses the dot product, all right? So it is more mathematically sound and more truthful when you're talking about how these energy equations are derived to actually write this particular equation in a different form. So the alternate form, or the more mathematically sound form, so better form of T equals 1/2 mv squared is T equals 1/2 m magnitude of v squared, which we just showed is T equals 1/2 m vector v dotted vector v. This is much more sound. And that is because you might not necessarily define your velocity components with rectangular coordinate system. Maybe you have a spherical coordinate system or a cylindrical coordinate system. And your dot product in those coordinates is slightly different, but if you know how to execute, you can end up getting yourself the kinetic energy without having to do a lot of rigmarole to figure out what it is. All right, so here, this definition is a lot more easy to work with when we're looking at sort of derivations. So easier to work with mathematically. All right. And that's good for us and nice for us because we're going to have to leverage this general mathematical form of this equation to do some of our derivations required to talk about how the kinetic energy of a rigid body is created. So we need this. Talk about energy of a rigid body. I'll be specific about this kinetic energy of a rigid body. All right. So this generally works for a particle of mass little m. Now, for a rigid body, we know a rigid body is a collection of tiny little particles. So the way that we've handled a collection of tiny little particles in the past, when we've done things like kinetics, is we've looked at contributions of all of those little particles on the body, added up all of those little contributions, and figured out then what is the whatever we're interested in the whole of that rigid body from the contributions of all of those little particles. That's exactly what we're going to do here. We're going to say that a rigid body is a collection of these tiny particles. They all individually have this kinetic energy, which is 1/2 mv dot v. And then we're going to sum up all of those contributions on the rigid body and see what the actual kinetic energy of the rigid body is in sort of final form. All right, so that's kind of where we're going with this next portion of the lecture, is talking about how to go from individual particles to a full-blown rigid body. So now moving to rigid body, we will add up contribution of kinetic energy from all points on body by integrating on the volume, or on the mass if you like. We're actually going to be integrating on the mass, but it's related to volume through density, so same difference. Okay, so general statement on what we're going to do next. Now we're going to do what I just talked about. Amazing how that works. Let's talk about what we're going to do, then let's do it, then let's talk about what we did. That's how teaching works, okay? Now you can all be professors. All right. See, it's not that hard, is it? All right. So now kinetic energy of a rigid body. All right. So recall our velocity analysis. Where we had relative velocities of multiple points on the body and kind of relating them, okay? So recall our velocity analysis where we had relative velocities between points. Something like the velocity of some point P is equal to the velocity of some other point, let's call it G, plus the angular velocity of the body crossed with the position vector that locates P from G. All right. Well, here obviously this is the velocity of some arbitrary point. And then on the right-hand side, we sort of broke this up into what was the velocity of translation of point G. And then here, this is the fixed axis rotation component of the velocity. So this is like if G were standing still and we were just rotating about G, what would the velocity of P be? So this is kind of like a fixed axis rotation. All right. Now, if we know that the kinetic energy of a particle, which would be like 1 point P, is 1/2 mv squared, all right, then we might expect if we move to a rigid body that we would have a kinetic energy of the rigid body, which might also look very similar to this, which is like some kinetic energy associated with translation here, plus some kinetic energy associated with rotation. All right, so moving to rigid body kinetic energy. Since kinetic energies are more or less like based on velocities of individual particles, we might expect that, let's say, the entire rigid body kinetic energy, right? So the kinetic energy of the rigid body, so I'll say TRB, is the kinetic energy of the translation of that rigid body. So the kinetic energy associated with the rigid body translation plus the kinetic energy associated with the rigid body rotation. So it's very analogous to like what we saw here, where velocities of certain points on this body were a combination of translation plus fixed axis rotation. We might expect something very similar for kinetic energy, which is a combination of translation and fixed axis rotation. All right, and that's exactly what we're going to see. So now let's get into it. All right, time to get your math pants on. Hopefully you have pants on at all. All right, go get your math pants on if you need to. I'll wait. Okay, you got them on? Good. So let's get mathy. All right, so now math. So this is the math of kinetic energy of a rigid body. All right, well, let's kind of lay the groundwork then. Let's say that we have some rigid body. With center of mass at point G. All right. And let's say it's moving through space. All right, so point G has velocity, which is VG. All right, so here's your mechanics potato. You've got some rigid body. It's got some center of gravity there, G. And this point G has some velocity as it moves through space, which we call V. Wonderful, great, fantastic, marvelous. All right, let's assume that now we're going to look at one individual point on this particular body as a specific case, and that particular point has a differential mass, which is dm. Okay, so look at point P with differential mass, which we'll call dm, right? And it'll be located at, obviously, a position vector which locates P from G. All right, so out here, let's call this point P, and it's located at location R, locating P from G. And let's say that this has mass, which is dm. So some very small minor differential mass. Okay, then with all that information, we can say that because this guy is moving through space, it might have some translation, might have some rotation, then this is also going to have some velocity of point P, which will be given by Vp. All right, so maybe this guy has velocity, which is over here, and this is my velocity at point P. All right. So with that information, we can define what is the differential kinetic energy at that particular point using our more formal mathematical definition. So the differential kinetic energy of P is, using our formal definition, we'll say that the differential kinetic energy of point P is 1/2 the mass, which here is the small mass dm, and then the velocity of P dot P. So Vp dot Vp. Okay, so this is my dot product here, Vp dot Vp. All right, so this is the differential kinetic energy of any arbitrary point P given the velocity of that general point, Vp, and some differential mass of that particular point, dm. Now we know a definition of the velocity of P relative to G. So we have this relative velocity equation. So let's relate Vp and Vg, meaning that the velocity here of point P is the velocity of G plus the angular velocity of this object crossed with the position vector, which locates P from G. All right, so let's say that this guy is rotating around with some angular velocity omega, and we happen to know what that is. Right? This might more easily be written, and we'll sort of write it in this way for now, is that this is the velocity of G plus the velocity of P relative to G. All right, where this is sort of this guy here. All right, so this is kind of our general setup. All right, then this term Vp dot Vp is a little complicated. All right, if we're splitting Vp into the translational component of G plus the fixed axis rotation component of P about G, this will be something like the velocity of G plus the velocity of P relative to G dotted with the velocity of G plus the velocity of P relative to G. Oh man, math. Getting mathy. Getting naughty in here. All right. So we kind of like FOIL this, right? First, outer, inner, last. And apply the rules of dot products. And you'll have something like Vg dot Vg plus 2 times Vg dotted with Vp relative to G plus velocity of P relative to G dotted with the velocity of P relative to G. All right. Now that we've gotten that out of the way, we can finally sum the contributions of all of the individual components on this body to get the total kinetic energy of this rigid body. So then, total kinetic energy on the body is the following. T on the rigid body is the integral on the mass of all of the differential energy components associated with all of the individual particles. So this is the integral of the differential kinetic energies of all of the particles P, which here is the integral on the mass of our sort of formal definition, 1/2 dm Vp dot Vp, or after substituting our little mathematical expression, we have here that this is the integral on the mass of 1/2 dm multiplied by all of this nonsense, which is Vg dotted Vg plus 2 times Vg dotted with Vp plus velocity of P relative to G dotted with velocity of P relative to G. All right, looks scary. And we're going to tackle that guy tomorrow. So this is where we'll pick up tomorrow. Make sure that you're kind of clear up to this point, sort of understanding how we got to where we got. And then we'll sort of break these individual pieces of this integral down one by one, talk about physically sort of what they mean, and kind of come up with our definition of the kinetic energy of a rigid body. So that's that for today. Thanks for coming. I'll stick around for a few minutes if people have questions.